As we look at these three standards, we must differentiate between relationships that are new to students and those with which they have prior experience. Each of the standards includes relationships that students have worked with previously, as well as relationships that are new to them. It is important to recognize that to prove requires students to formally prove their relationships by developing viable deductive arguments. For relationships where students have prior knowledge and experience, activities in class may go directly to the formal proof. In the case of new relationships, students need the opportunity to explore and make conjectures through hands-on investigations prior to proving the relationship. First-hand experience provides the opportunity to notice patterns in relationships and to call on prior knowledge before tackling a more formal deductive argument. In this video, we look at examples of both of these situations. First, we see a student exploring the properties of a triangle midsegment for the first time. This exploratory experience leads nicely into a conversation of how to build a proof of the relationships the student discovers. In the second example, we see the students applying prior knowledge of congruent triangles and angles formed by parallel lines. As you watch the students' work, be on the lookout for the standards for mathematical practice in action. Standards 1, 3, and 6 are intrinsic to proofs.
So as you look at that construction, what do you think might be true about the mid-segment?
The mid-segment MN would be half of the segment BC.
Do you have a reason that you feel that way?
Well, I mean, it's the mid-segment, so I figured it might be in the middle. You can measure the lengths of the segment MN and BC and compare them.
Does that seem like it's half to you?
Looks like it. Yes, but couldn't we change it and see if it's true?
What do you think as you look at the numbers?
It still looks to be true.
Okay, so you have the same values. Why don't you go ahead and move point C around and see if that stays true. So is your 1/2 relationship staying true as you move your points?
Yes.
Okay, well, so why don't you move A and make it go really different? Is it staying true?
Yes.
Is it changing at all?
Well, the numbers are changing, but the relationship isn't.
Is the number changing?
Well, oh, no. It looks like segment MN is parallel to segment BC.
Okay, what did you see that made you think that?
Well, these are corresponding angles, I think. So,
Okay, so let's be really specific with that. Name your angles and let's look at that.
angle M appears to be corresponding with angle B, so they would equal 180 degrees, and they would be parallel.
Because I see a bunch of angle M's in that triangle.
The angle NMB.
Okay, so you have a measurement there. Now, what angle did you want to look at it in comparison to?
Angle B. So, well, angle MBC.
So let's go ahead and measure that one. Now, you said you thought those were corresponding angles, or are they in the same relative position?
Well, they would both be, if you're looking at a transversal, they would both be inside and on one side.
Okay, so on one side of a transversal is called...
Same side?
Okay, and you just said they're both inside between the ones that you're thinking are parallel?
Yes.
So they're not corresponding, they're...
Same side interior.
What do we know to be true? If same side interior angles are supplementary, what does that tell you about the segments or the lines that you have?
That they're parallel?
All of the relationships that you saw before stay true?
Yes.
What we're trying to prove is that quadrilateral BCD is a parallelogram. And what we tend to look for in parallelograms is that there are two pairs of parallel sides. And what we have given to us is that line segment BC is congruent to line segment ED, and that line segment BC is also parallel to line segment ED.
Angle EDC and angle BCD congruent because parallel lines imply that alternate interior angles are congruent.
That line segment DC and line segment CD are congruent because of the reflexive property.
Then we could say that triangle EDC is congruent to triangle BCD by side angle side.
These sides would have to be congruent. Oh. Well, they would be congruent as well. And that the angles ECD and BDC are congruent
So how do you know both of those things?
because of CPCTC.
All right, so now you marked them with one angle. So are you saying that those two pieces are congruent? Okay, now.
Yeah.
All right. So then with that information you just added from CPCTC, why did you want to do that?
Because alternate anterior angles are congruent, that would imply that line segment CE and segment DB are parallel as well.
So is that enough to know that you have a parallelogram?
Yes, because we now have two pairs of parallel sides, and that opposite sides are congruent.
So did you need all of that?
No, we would be fine with the two pairs of parallel sides. So.
Okay.